Morning, friends. Very good morning and welcome in the next video lecture of uh, electromagnetic field theory. In this video lecture, we will study about the electric flux density and Gauss law. In previous lecture, we have already discussed about the electric charge, Coulomb's law, electric pole intensity or electric field intensity. In this electric field intensity, we have discussed the line charge, volume charge, surface charge or space or differential length charge, point charge. So in a previous lecture, we have already discussed about the charge and electric field intensity and the relationship between the charge and electric field intensity and Coulomb's law. And we have already discussed the some rules regarding the electromagnetic field, or electric intensity. Today's lecture is based on the electric flux density Gauss law. Prerequisites to learn this lecture, student able to understand the vector calculus. They have to clear the calculus, mathematical expressions, dot product, cross product, Coulomb's law, electric field intensity, and they are also able to understand the electric charge, charge density. So these are the prerequisites for understanding of today's lecture. The course focus is the electromagnetic field theory. This course is deal to develop the foundation of electromagnetic field theory. The learning objective of this video lecture is that the student will learn and understand the concept of electric charge, charge density, electric flux density, Gauss law. They are also able to understand the Maxwell equations. In the previous lecture, we have already discussed the four Maxwell relationships. So, Gauss law and electric flux density is the law to generate the Maxwell equations. The application of the Gauss law and electric field intensity in the Maxwell equations. Today's lecture is based on the application of the electrostatic field theory or electric field intensity. In the last, we will discuss the several application of electric field intensity. And in the last of this video lecture, we have some multiple choice questions. These are the textbooks and the other recommended books for electromagnetic field theory. SADIQ is the book which is published by the Tata McGrail, and the title of this book is The Principle of Electromagnetic. The main outcome of this video lecture is to clear the concept of the electric flux density, Gauss law, and the application of the Gauss law in the Maxwell equations. On the completion of this video lecture, student will also understand the concept of electric flux density and the Gauss law and the application of the electrostatics in the several areas where we applied the electrostatic field theory in the daily lives. Now we have come to the introduction about the electric flux density. What is the electric flux density? The field intensity or simply electric field gives the strength of field at a particular point. The electric field depends on the material media because which is based or related to epsilon naught, and epsilon naught and epsilon r, that is relative permittivity of the medium. So electric field is the based on the material media in which the field is being considered. So electric field is a quantity which gives the field strength at a particular medium or particular point in a medium. The flux density vector is defined to be independent of the material medium. So flux density is not depend on the medium. It is the independent of medium. For a linear isotropic medium under the consideration, the flux density vector is defined as B equal to epsilon naught E. E is the flux density vector, and E is the electric field intensity. Epsilon naught is the relative, it is the permittivity of material. The electric flux phi as phi equal to the surface integral of T dot ds in the form of integral form. So psi is the electric flux, and D is the electric flux density vector. Consider a set of the concentric metallic spheres, the outer one consisting of two hemispheres, which could be firmly claimed together. First, with the equipment dismantled, the inner sphere was given a non-positive charge. Second, the hemispheres were claimed together around the charge sphere with about 2 centimeters of the dielectric material between them. The outer sphere was discharged, connecting it momentarily to the ground. The outer sphere was separated carefully using tools made up of insulating material in order not to disturb the induced charge on each hemisphere and negative induced charge on each hemisphere was measured. This is the Faraday's experiment. In the Faraday experiment, we have charged sphere, that is the positive charge, and metal and insulator. So metal is providing the field, or it is grounding, because charge is on the sphere produce the electromagnetic fields. It can be found that the total charge on the outer charge was equal in the magnitude to the original charge placed on inner sphere, and this was true regardless of the dielectric material separating the two spheres. There was some sort of a displacement from the inner sphere to the outer sphere, which was independent of the medium. This as the displacement flux density and electrical flux is represented by psi. So psi equal to the charge, that is the Q. The electrical flux is measured in the coulombs. The unit of the electrical flux is the same as coulomb, the unit of the charge. The electric flux density is represented by the letter T because of the nature that was given initially, displacement flux density. Displacement flux density. Because charge is displaced in the sphere. So the flux density is represented by the charge Q, that is the flux, electric flux density is represented by the D, and electric flux is represented by the Q, and it is equal to the psi and in the coulombs. The electrical flux density T is a vector. It is a vector quantity and is a member of the flux density class of vector fields. The direction of the D at a point is the direction of the flux lines at that point. And the magnitude is given by the number of the flux lines crossing a surface normal to the lines divided the surface area. The magnitude is given by the number of the flux lines crossing a surface normal to the lines divided the surface area. This is the electric flux in the region between a pair of the charge concentric spheres. In this figure, we understand that the R is equal to the A, radius for inner sphere, and R equal to the B is the outer spheres. So charge is moving from plus to minus, means inner to outer, and the metallic conducting spheres has the outer body is the metallic, and in between of the two spheres we have a dielectric or insulating materials. So this is the phenomena to develop the electric flux in the region between a pair of charge concentric spheres. So this sphere is concentrate with the charge. The electric flux density is the radial direction, in the radial direction, and has a value of E, where R is the radial distance is the A, is equal to Q upon 4 pi A square in the direction of AR, because B is the vector quantity. B R equal to the B equal to the Q upon 4 pi B square in the direction of the AR, and at a radial distance of the R, that is R is less than to the B or equal to the B, and it is greater than to the A or equal to the B. So now we have calculated the flux density, electrical flux density at the distance R, that D is equal to the Q upon 4 pi R square in the direction of AR, vector, unit vector AR. If compare this result with the equation for electric field intensity of a point charge in the free space, that is electric field intensity is equal to the q upon 4 pi epsilon naught r square in the direction of kr. It is also a vector quantity which we have already studied in the previous lectures. So the electric field intensity will depend on the medium, but electric flux density is not depend on medium. So in the free space, on the comparison of the two equations, that is the electric flux density as well as electric field intensity, we get the relationship of charge density, electric flux density is equal to the D equal to epsilon naught T. The figure below shows that clearly what is the flux passing through an open surface. The figure third shows that the electric flux through an open surface. So through which we are able to understand that the how much of the flux is passing through a open window or open surface. Figure E shows that the air flows. Figure B shows the flux, and figure C shows the electric flux, and figure D shows the complete electric flux from a window or a surface, open surface. So this figure shows that the electric flux through an open surface, passing through an open surface, and we are able to understand that how the electric flux density is related with the electric field intensity. In the next section, we have the Gauss law. The Gauss law is defined as the Gauss law is the one of the fundamental law of electromagnetism, and it states that a total electric flux through a closed surface is equal to the total charge enclosed by the surface. Yes, it states that the total electric flux through a closed surface is equal to the total charge enclosed by surface. Total charge enclosed by surface. So here we have the figure shows that V is the density and theta is the angle, and we have a cone in the closed surface, and ds is the surface area in the and theta and an is the normal vector. Gauss law constitutes one of the fundamental law of electromagnetism. It also developed the Maxwell equations. All the Maxwell equation is based on the Gauss law. Gauss law is the particularly useful in the in computing or where the charge distribution has some symmetry. Now we have the application area of electrostatics theory or electric field intensity. In the previous lectures, we have already discussed some important name of the uh, application. That is the electric force in the biology and Xerox copy and printers, scanners. These are the daily life application of our electrostatic field. So we are going to discuss more in the more detail and insight of the application or area of electrostatics. or electric field intensity. So the first application of this is the electric forces in the biology. Classical electrostatics has an important role to play in modern molecular biology. Large molecules such as the proteins, nucleic acids, and so on, so important to life, are usually electrically charged. DNA itself is highly charged. It is the electrostatic force that not only holds the molecule together but gives the molecular structures and the strength. So electric force is developed in our body. So electric static force not holds two molecular together, but gives the molecular structure to strength. So this is the first application of electrostatics. Second application of the electrostatic is the polarity of the water molecules. The best example of this charge screening is the water molecules. Water molecules consist the positive and the negative charges. So there is the electrostatic field is developed, represented as H2. Water is represented by H2O. Water is a strongly polar molecule. It's 10 electrons, that is the 8 from the oxygens and 2 from hydrogens. Two atoms from hydrogen and from oxygen. So total 10 electrons tends to remain closer to the oxygen nucleus than the hydrogen nucleus. This creates the two centers of the equal and opposite charges called a dipole. So then the dipole is formed. So there will electrostatic field will also develop. So in this water molecule, positive and negative charges are developed, and there will be the motion of the charges. They will attract and repel to each other. So dipole is formed in the water molecules. Next application area of the electrostatic is the Earth electric field. A near uniform electric field of approximately 150 newtons uh, per coulomb directed to downwards surrounding the earth, with the magnitude increasing slightly as get closer to the surface. The earth electric field is another application of the electrostatic application. So in this application, the earth is behaved just like a dipole, and it will generate the polarity, and it will also generate electrostatic field. So near the uniform electric field is approximately 150 Newton per coulomb directed downwards surrounds the earth, with the magnitude increasingly slightly as get closer to the surface. When we move to the surface of the earth, then there will be magnitude increase slightly as compared to down to earth. At around 100 kilometers above the surface of the earth, we have a layer, that is the ionosphere layer, and called a charged particles. So that's why its name is ionosphere layer, about the 100 kilometer from the earth's surface. So this has the polarity. So the charged particles are available in the ionosphere layers. Ionosphere is responsible for a range of the phenomena, including the electric field surrounding Earth in pair whether the ionosphere is the positive and the Earth largely negative, maintaining the electric field. So, in the normal weather conditions, there is the electric field or electric potential is developed in between the surface of the earth and the ionosphere layer. Because ionosphere layer is behaved just like a positive charge, and our earth surface or the downward earth surround the earth is behaved just like a negative charge to maintaining the electric field intensity. So this is the application area of Earth's electric field. This is the picture of the lightning. It is also the application area of the electrostatic. So through lightning, electrostatic field is developed or electric field is intensity is developed. Application of the conductors. This is the a sharp conductor and its electric field. Uh, this conductor is sharply at the top as compared to the bottom, and it has a high density of the electric field charge at the top. On a very sharply curved surface, such as shown above figure, the charges are so concentrated. Means if you have any sharply curved surface, and there will be the charge concentration, charge density will be very high as compared to the other point. At that point, the resulting the electric field can be great enough to remove them from the surface. Lightning rods work best when they are most pointed. Another example is the lightning rods, how they work. So lightning rod works best when they are most pointed at the end because of the charge concentrated at that point, and they will produce the electric field intensity. So there will be lightning. The large charge is created in storm clouds induce an opposite charge on a building that can result in a lightning bolt hitting the building. So, in the thunderstorms or the storm clouds, they produce the opposite charge on the building. If thunderstorm produce the positive charge and the building having a negative charge, so opposite charge is attracted to each other. So they will attract and hitting the building. So this is the another application to the electrostatic field. The induced charge is bled away continually by lighting rods, preventing the more dramatic lightning strikes. So this is the another application of electromagnetic field theory in the conductors. We are understanding the how the lightning rods works, and storm clouds are attracted by the building uh, because we have opposite charges on the building. So the conductor have charge concentration at the uh, point or curved surfaces. Next application of our electrostatic field theory is that the applicable in the Van de Graaff generators. Van de Graaff generators, or it is known as the Van de Graaff, are not only the spectacular devices used to demonstrate the high voltage due to static electricity, they are also used for serious research. When the brass utilize both smooth and pointed surfaces and conductors and insulators to generate large static charges and hence large voltages. Pointed surfaces and the conductors and the insulators to generate the large static charges and hence the large voltage is developed because there is the insulator, conductor and the pointed surfaces. So static charges is pretty low. This is the diagram shows that the Van de Graaff generators, and in this we have a conductor having a positive charges inside of the uh, conductors, and we have a ion sources that is the which generates the ions, and again we have a flexible non-conductive belt to experimental areas, and we have a insulators, then we have a ground, and we have a supply voltage. So this is the Van de Graaff generator is what to generate the electricity. A very large excess charges can be deposited on the sphere. You can understand from this figure the very large charge density is deposited on the sphere because it moves quickly to the outer surface. See, this is moved to quickly outer surface. Practical limits arise because the large electric field polarize and eventually ionize surrounding materials, creating a free charges that neutralize excess charge or allow it to escape. Practical limits arise because the large electric field polarize and eventually the ionize surrounding the materials, creating free charges that neutralize the excess charge and allow it to escape. Nevertheless, voltages of the 15 million volts are well within the practical limits. The next application area of the electrostatic is the Xerox or geographies. Most copy machines or Xerox copy machines use an electrostatic principle or electrostatic process called the geographies. Here we have a porotron or a drum, that is the selenium on aluminum drum. First stage, charging the drum. Second stage, the positive image made on drum. Suppose we have to print a 3. So positive image is made on the drum. After that, on the aluminum drum, we developed the negative image or negatively charged toner that will generate the negative image of positive charge, toner attracted to image. Fourth stage, toner pulled from the drum by highly charged paper. So this is the complete mechanism of geography or Xerox machine or Xerox copy. A selenium coated aluminum drum is sprayed with positive charge from points on a device called the porotron. Selenium is an insulator when in the dark and a conductor when exposed to light in the first stage of the lithography process. The conducting aluminum drum is grounded so that a negative charge is induced under the thin film of uniformly positively charged selenium. In the second stage, the surface of drum is exposed to image of whatever is to be copied. Means we develop a positive image of uh, our required document. After that, it developed a negative copy by selenium insulators, and the image is produced on the paper. Laser printers is the another application or area of electrostatics. Laser printers use the xerographic process to make uh, high quality images on paper. Employing a laser to produce an image on the photoconducting drum as shown in the figure. This is the figure. Computer, laser, and optics device is produced the image on the paper, that is the path of the lasers and remaining charged region. In its most common application, the laser printer receives output from the computers, and it can achieve high quality output because of the precision with which laser light can be controlled. Next application is the inkjet printers. This is the our laser printer, how the printing is developed by laser. Next is the inkjet printers and the electrostatic printing. An inkjet printer commonly used to print the computer generated text and graphics. Also applies electrostatics theory. A nozzle makes a fine spray of ink droplets, which are then given an electrostatic charge. Once charged, the droplets can be directed using pairs of the charge plates with great precision to form letters and images on the paper. So this is the example or picture to show that the inkjet printer, how inkjet is print. Ink nozzle, then charging electrodes, deflection plates, and paper. And we have emitters and ink reservoirs. So inkjet printer, a nozzle makes a fine spray of thin ink droplets, which are then given an electrostatic charge. Once the charge, the droplets can be directed using the pair of the charge plates with great precision to form a letter and the image on the paper. So deflection plates and charging electrodes is used. Nozzle produce the image fine spray of the tiny ink droplets and which are given to the electrostatic charge. So electrostatic gun is producing a charges. Another application area of the electrostatic is the smoke precipitators, and electrostatic air cleaners or cleaning. Another important application of electrostatics is found in air cleaners, both large and small. If you are going to use it in the house, it is the small area, and if you are going to in industry and factories, this is the large area which smoke precipitors, and electrostatic air cleaners is used. The electrostatic part of the process places the excess, usually the positive charge, on smoke, dust, pollen, and other particles in the air, and then passes the air through an oppositely charged grid that attracts and retains the charged particles. This is the picture of the electrostatic precipitators. Precipitators will attract the opposite charges. So here we have a initial filter and neutral particles. Then we have a positive charging grids, and we have a negative charging grids. So positive charges is attracted by that is the positive charges in the polluted airs, and dust and smoke particles having a positive charge, and negative charge grid will attract this, and finally they will filter the air and produce the clean particle free airs. So this is the application of electrostatic precipitators, which produce the clean and smoke-free airs. So electrostatic air cleaning is the application of electrostatic, and these type of the air cleaner is generally used in the air and heaters, air AC in, and AC heaters. In the next section, we have some multiple choice question on the basis of Gauss law and application of the electrostatic field theory and electric flux density. Gauss law is the applicable for A, point charge, B, sheet charge, C, line charge, D, point, sheet, and line charge. Explanation of this question is that Gauss law states that the total electric flux through any closed surface is equal to the charge enclosed by that surface. Hence, it is the applicable for all points, source, and volume. Total electric flux through any closed surface is equal to the charge enclosed by that surface. Question number 2 is the that total electric flux through any closed surface is equal to the charge enclosed by that surface divided by permittivity. This is the statement for A, Gauss law, B, Lenz law, C, Coulomb's law, D, Faraday law. Third question, the electric flux density is a function of A, volume, B, charge, C, current, D, voltage. Electric flux density is the charge per unit area, hence it is the function of charge and not only the other values. Question number 4, as charge increases, what happens to flux density? A, increases, B, decreases, C, remains constant, D, become 0. The electric flux density is the charge per unit area. The expression for flux density is D is equal to the Q upon A. Electric flux is directly proportional to the charge. Hence, as charge increases, electric flux also increases. As area increases, what happens to electric flux density? A increases, B decreases, C remain constant, D becomes 0. Electric flux is inversely proportional to the area increases, electric flux decreases. Which among the following is the correct expression for electric flux density? B is equal to the epsilon of into E. B is equal to the epsilon upon E. C D square equal to the epsilon into E. D is equal to the epsilon into E square. Electric flux density is directly proportional to the electric field. Epsilon, that is the permittivity of the free space, being the constant of proportionality. Hence, the correct answer of this question is A. Question number 7. The strength of the electric field is A. Directly proportional to the force applied. B. Inversely proportional to the force applied. C. Directly proportional to the square of the force applied. D. Inversely proportional to the square of the force applied. The electric field intensity is the force per unit charge. Hence, it is directly proportional to the force applied. Question number 8. The force applied to the conductor is the 10 Newton if the charge in the conductor is 5C. What is the electric field intensity? So electric field intensity is the F upon Q. So F is the 10 and conductor charge is 5. So it will comes 2 volt per meter. What is the electric flux density in the free space if the electric field intensity is 1 volt per meter? So correct answer is the 8.85 into 10 to the power minus 12 coulombs per meter square. Because the D is the epsilon into epsilon into E, where epsilon is the relative permittivity of medium. Last, if the charge in a conductor is 16C and the area of the cross section is 4 meters square, calculate the electric flux density. So electric flux density is the Q upon A, where the Q is the 16C and charge and area is the 4, that is the 4 coulomb per meter square is the final answer of this question. So the conclusion of today's lecture is that today we have studied very important concept of Gauss law and electric flux density, electric flux in the Gauss law application in the Maxwell equations. And in the last section, we have already discussed in this video lecture about the application of the electrostatic field or electrostatics. We have several applications of electrostatic fields or electric field intensity. So we have already already discussed the application area of electrostatics in very vast and very elaborate manner. So today's lecture is based on Gauss law and electric field intensity. Thank you.